So I'm going to present to you ViTAL, a vision transformer-based accelerator for real-time lineage assignment for viral pathogens. Okay, so let's begin with that. So basically, we're going to talk about lineages, and I'm going to define what lineage is. So lineage is defined by a genome base, let's say, and a set of variants. So, for example, the SARS-CoV-2 genome that was sequenced in Wuhan in 2019 was a genomic base, and a lineage of it is, for example, B117 or Omicron. So let's set up the problem. During the COVID-19 pandemic, we have witnessed an unprecedented effort to surveil the SARS-CoV-2 virus, mainly by tracing its variants and lineages. So that's important because lots of reasons, such that detecting transmission dynamics and more accurate health response. So what's the problem with that? So the process of lineage assignment uses whole genome sequencing, which can take several days, and the amount of data generated poses a great pressure on the underneath infrastructure, such as sequencing machines and computer infrastructures. As a reason of that, only a small subset of samples are analyzed using whole genome sequencing. So the problem it causes is inaccurate map of the viruses, of the virus spread, and delayed WHO intervention. Okay, so to alleviate this issue, one can use low coverage whole genome sequencing. So basically, this is a new sequencing method that sequences simultaneously at the same machine many samples, while as opposed to, let's say, pool sequencing, it preserves the information of the origins of the sample. So if we compare the low coverage whole genome sequencing to vanilla whole genome sequencing, we get enhanced throughput. We get also reduced sequencing cost per sample, that is, but there is no free meals here, and basically we get sparse data. So that's a bummer. How does sparse data is represented? So let's look at this animation here. The black line is the genome, is the original genome, and the purple lines is the sequenced fragments, the reads, and sequencing using low coverage whole genome sequencing simply results in a reduced coverage, which results in sparse areas that basically did not get sequenced. Okay, so we want to use low coverage whole genome sequencing to alleviate the throughput and scale up, but we get sparse data, and we wanted to test how state-of-the-art tools performs with that kind of data. So we tested Usher, which is a classifier for SARS-CoV-2. It basically performed very, very well when it was pitted against high coverage levels. But as we reduced the coverage level, we saw that the accuracy was affected very much. So we wanted to solve this, and we proposed using the vision transformer. Vision transformer is simply the transformer encoder with some modifications. I won't get into it, but we used it because our intuition was that we want to learn some generic features from the genome even if data is lost. So the attention mechanism is a great candidate to do that because it can focus on some regions that may guide us knowing where what's the lineage is. So as you know, a deep neural network expects numerical vectors as an input, but genome is a string. To convert it, we pre-processed it using the minhash scheme. So minhash basically extracts k-mers from the genome. We get these k-mers and we extend them. After that, we one-hot encode the bases. So A is encoded to 1000, C is encoded to 0100, and so on. So the complete architecture simply looks like this. We get an assembled genome, we transform it, we extract features from it using the minhash and one-hot encoding, and then we feed it to the modified vision transformer. These are some parameters that we used, hyperparameters that we used. We use 16 k-mer size of 16, and we extend it to be a fragment of 256. etc. There's some hyperparameters here, but that's not so important. And we tested our design after we trained the networks, and we got that the black lines is the performance of ViTAL, our algorithm, and we got that even at let's say for Illumina high sequencing simulator, it performed at 1x coverage level, it performed almost as good as Usher at 8 times coverage. So that's an 8 times reduction, and we can deduce that we can scale up the processing of genomes by 8 times. Okay, so after we've seen after we've seen what the model is capable of, we decided to test it and see how it was doing in detecting novel lineages. To do that, we trained the model on lineages published before October 2021, and we tested it against lineages published after. What we get is this. Simply, if we feed the model with a lineage that the model was trained on, the output probability of the model, we observed it was almost around 100%, in the neighborhood of 95 to 100%. Whereas if we feed the model in a lineage that it wasn't trained on, it was ranging between 65 till 100. And moreover, if we define a threshold at, let's say, 90%, we yield 85% success rate in detecting new lineages. So that's basically it.